Tonight, we're going to explore a question so old, so enormous, and so mysterious that it sits right at the edge of human understanding. It's a question that seems simple when you first hear it, almost childlike, almost innocent. But the moment you try to answer it, the ground shifts beneath you. Time bends, space dissolves, and everything you think you know about the universe begins to unravel. Because we're not just exploring an event, we're exploring a boundary, the ultimate boundary, the limit where our physics, our mathematics, and even our imagination begin to fail. And yet, somehow, this question keeps calling to us, whispering, pulling us closer, asking us to look deeper than we ever have before. Before we begin this journey, if you find these kinds of explorations meaningful or calming, or even just comforting to listen to, a quick like or subscribe truly helps me continue making these long, deep dives into the cosmos. It means more than you know. But for now, just relax. Let everything slow down. This is going to be a quiet, gentle descent into one of the greatest mysteries of existence. Let's start not with the universe, but with something more familiar, with beginnings. Because every story you know has one. Every book, every memory, every life, everything you've ever experienced has a moment before which there was nothing, and after which everything unfolds. We're used to thinking this way. It's built into our language, our logic, our storytelling, our sense of time. But the universe doesn't behave like a story. It doesn't follow the rules we're used to. And when we ask the universe a seemingly simple question, what happened before everything? The universe answers us in a way that feels almost like a riddle wrapped in darkness, in silence, in a kind of cosmic stillness we're not built to comprehend. To even begin exploring this question, we first have to understand the moment we're trying to look past. The moment we call the Big Bang. A moment we often imagine as an explosion, a sudden burst of energy expanding into an empty void. But that picture is wrong. Deeply wrong, in fact. The Big Bang wasn't an explosion in space. It was the expansion of space itself. The stretching of the fabric of reality from a state so dense, so hot, so compressed that our physics can't describe it. When we try to see farther back than this moment, time stops behaving the way we expect. The equations that work everywhere else in the universe start collapsing. They overflow, diverge, break. They tell us that density becomes infinite, temperature becomes infinite, gravity becomes infinite. But infinities in physics are almost never real. They're signs of something deeper, something hidden, something we don't yet understand. As strange as it sounds, the Big Bang isn't the beginning of the universe. It's the beginning of the universe we know how to describe, the beginning of the laws of physics as we experience them, the boundary of our scientific vision. Beyond that limit lies a kind of cosmic fog, not empty, not silent, just unknown, and perhaps unknowable. Imagine standing at the edge of a vast ocean at night. You can hear the waves. You can smell the salt in the air. You can feel the cool wind on your skin. But the ocean itself is completely invisible. You know it's there, stretching far beyond the horizon. But you can't see where it begins or ends. All you know is that you're standing at the shore of something unimaginably larger than yourself. That's where we are with the Big Bang, standing on the shore of a vast cosmic sea, knowing that something came before the moment we call the beginning, but unable to see what it was. And yet, we can hear the faint echoes of it. We can feel its presence in the laws of physics. We can detect its fingerprints in the structure of the universe. Not clearly, not directly, but hints, clues, whispers. To understand what might have come before our universe, we need to move slowly, carefully, because the answers aren't like the answers we're used to. They don't fit neatly into our categories of time and space. They don't follow our rules. So I want you to think of this journey not as a search for the truth, but as an exploration of possibilities. A quiet walk through different ideas, each one offering a glimpse of what reality might have been like before time itself began. Let's start with the simplest idea, and the hardest one to accept. It's the idea that there was no before, that time itself began at the moment of the Big Bang. According to this view, asking what happened before the universe existed is like asking what's north of the North Pole. It's not that the answer is hidden, it's that the question doesn't make sense in the first place. There is no north of the North Pole. There is nothing before time. This idea isn't just philosophical. It comes directly from Einstein's equations, from the mathematics of general relativity. Time, according to relativity, is not separate from space. It's woven into the same fabric, space-time, a single continuous structure. So when the Big Bang occurred, it wasn't just matter and energy that burst into existence. It was time itself. Before that moment, there was no before, because before requires time, and time hadn't begun. This is the most traditional view, the oldest, the simplest, but it's also the one that feels the most unsettling, because it denies us the idea of a cause, a reason, a prior state. And as humans, we're not comfortable with that. We crave beginnings. We crave explanations. We want to know why. But our desire for a reason doesn't guarantee that the universe will give us one. And yet, even this idea, the idea that time simply begins, might not be the whole story. Because as soon as we look deeper, the universe begins offering us clues that something may have existed before our beginning. Something hidden, something ancient, something we're only now beginning to glimpse. And that's where we'll go next. If the first idea is that nothing came before the universe, the second idea is the opposite. The idea that something did exist before the Big Bang. Not a universe like ours, not stars or galaxies, not even space or time as we understand them, but a deeper reality, a kind of cosmic foundation, a stage upon which universes rise and fall, a realm where our Big Bang is just one event among many. This possibility begins with a simple observation. When we study the universe carefully, really carefully, we start to find patterns that shouldn't be there if the Big Bang were a true beginning. Patterns that suggest continuity, memory, structure, as if our universe inherited something from a time before its birth. One of those clues comes from the smoothness of the universe itself. When we look across the cosmos, we find that matter is spread out astonishingly evenly. So evenly that it defies explanation. Because at the moment of the Big Bang, there was no communication between distant regions of space. They were too far apart. There wasn't enough time for anything, not matter, not light, not heat, to travel between them. And yet somehow, the entire universe began at almost the same temperature, almost the same density, almost perfectly balanced. It's as if the universe began not in chaos, but in perfect coordination, like a symphony that starts with every instrument already in tune. That's strange, deeply strange, and it suggests something profound. Something set the initial conditions. Something prepared the universe before it expanded. Something shaped the state of reality before our physics came into play. Could that something be a previous universe? Could our cosmos be the echo of an older world that came before? Let's explore that idea. Slowly, carefully, with open curiosity. One of the oldest ideas in cosmology is the idea of a cyclic universe, a universe that expands, collapses, and is reborn again and again in an endless rhythm, like a cosmic heartbeat. Not one universe, but many. Not one beginning, but infinite beginnings stretching back forever. In this picture, the Big Bang wasn't the start of everything. It was simply the transition. The moment one universe reached its end, collapsed under its own gravity, and rebounded, giving birth to the universe we inhabit today. If this idea is true, then our universe carries the faint genetic imprint of the universe that came before it, just as you carry traits passed down from ancestors you've never met. But there's a problem, a profound one. Physics tells us that if the previous universe collapsed, the collapse would end in a singularity, an infinitely small, infinitely dense point. And when a singularity forms, information is lost. Completely, permanently, wiped away. So if our universe was born from such a collapse, how could it remember anything from before? And this is where modern physics begins to surprise us, because evidence is emerging that singularities might not be real, that they are mathematical artifacts, signs that our equations are incomplete, not physical realities. And if singularities aren't real, then the collapse of a previous universe might not compress information into oblivion. It might transform it, reshape it, preserve it in subtle ways that we see today in the smoothness of the cosmic microwave background, in the distribution of galaxies, in the curvature of space. If this is correct, then our universe might be the child of an older universe. Not a perfect copy, not a remnant, but an heir, a continuation. Another version of this idea doesn't involve collapse at all. It imagines that universes come into being through a process called quantum tunneling. In quantum physics, particles can sometimes pass through barriers they shouldn't be able to cross. Matter slips into places it simply shouldn't be. Now imagine applying that idea not to particles, but to entire universes. A universe might tunnel out of a previous one, emerging like a bubble rising from a deeper ocean. A bubble with its own space-time, its own laws of physics, its own beginning. In this model, the universe we live in exists because another universe permitted its birth. And that universe existed because yet another one permitted its birth, and so on, stretching backward not to a beginning, but to a chain without a first link. This idea is unsettling, but strangely comforting, because it means the cosmos is not a one-time event, not a fragile miracle that happened once and could have easily failed. It means the universe is generative, fertile, creative. It means the universe makes universes. But maybe the deepest possibility, the one that challenges us the most, is that the universe before the Big Bang wasn't a universe at all, not in the way we experience it. Not something with space or time or matter or energy. Maybe before the Big Bang, there was only a kind of potential, a state with no dimensions, no change, no flow of time, a timeless reality that contains every possible future, every possible universe, every possible history, but nothing actualized. A state where everything that could exist waits, until suddenly, it doesn't wait anymore. Something happens. A symmetry breaks. A fluctuation appears in the quantum void. A ripple forms in the fabric of possibility. And that ripple expands, inflates, and becomes space and time, becomes our universe, becomes us. Right now, scientists are searching for clues that might reveal what existed before the universe as we know it. These clues would be incredibly faint, hidden in the oldest light in the cosmos, buried in the gravitational waves that ripple across space-time, encoded in the fine structure of the cosmic microwave background. We call this search cosmic archaeology, looking not for fossils of ancient creatures, but fossils of ancient universes. And here's the astonishing thing. We may have already found some hints, small anomalies in the background radiation, patterns that shouldn't exist, cold spots, elliptical distortions, regions that look like bruises left by collisions with other universes. Are these illusions, statistical noise, or the fingerprints of a time before time? We don't know yet, but the fact that these questions can even be asked tells us something profound, that the boundary of the Big Bang is not a wall. It's a door we're only just beginning to understand how to open. To understand what might have existed before our universe, we need to examine the moment of creation itself, not the expansion that followed, but the instant the universe transitioned from nothing to something, from potential to reality. This moment is hidden behind a veil of mathematics we're only beginning to understand. And the key to lifting that veil may lie in quantum physics, the strange set of rules that govern the smallest scales of existence. When we think about the Big Bang, we often imagine a singular explosion, a blast of energy bursting from an infinitely small point. But modern cosmology doesn't see it that way. Instead, the Big Bang was a transformation, a phase change, a shift from a state with no recognizable space or time into a universe with expanding space and flowing time. Picture a landscape covered in a perfectly still ocean. No waves, no currents, no ripples. Completely motionless, completely calm. Now imagine a single tiny ripple appearing, perhaps created by a fluctuation so small it normally wouldn't matter. A vibration from deep beneath the surface, a disturbance that changes everything. That ripple expands outward, creating larger and larger waves, eventually transforming the entire ocean. Our universe may be that ripple, a quantum fluctuation in a deeper cosmic field, a tiny vibration that grew, not into a wave of water, but into space itself, into galaxies, stars, atoms, life, thought, conscious minds trying to understand their own origins. But what was the ocean beneath that ripple? What existed before the fluctuation? Quantum physics gives us a surprising answer, an answer that feels like it shouldn't be allowed, and yet it is, because the laws of physics permit it. Before the universe existed, there may have been nothing. But in physics, nothing is not empty. Nothingness is unstable. It teems with energy. It vibrates. It fluctuates. Virtual particles appear and disappear constantly, popping in and out of existence too quickly to be observed directly. The vacuum is alive with potential. It is a stage waiting for reality to step onto it. And under the right conditions, a fluctuation in this restless nothingness can create not particles, but a universe. Not a small spark of matter, but a self-contained bubble of space-time that grows, expands, inflates, and becomes everything. This is one of the leading ideas in modern cosmology. Our universe as a quantum seed, born not out of a previous universe, but out of a deeper quantum vacuum that exists outside of space and time as we know them. To understand this transformation, we need to talk about inflation. Not economic inflation, cosmic inflation. The briefest, fastest expansion in the history of reality. According to inflation theory, the entire observable universe, the galaxies, the stars, the planets, the atoms that make up your body, all of it was once smaller than a single atom, smaller than a proton, smaller than anything we can physically imagine. And in a fraction of a fraction of a fraction of a second, that tiny region of space expanded exponentially. Not slowly, not gradually, but explosively, doubling in size over and over again, trillions of times in less than an instant. Where did this energy come from? And what triggered the inflation? One idea is that inflation began when a quantum field, a kind of invisible energy field permeating reality, transitioned from an unstable state to a stable one. During this transition, it released an enormous burst of energy, enough energy to create space, enough energy to drive expansion, enough energy to become everything. But here's the strange part. Quantum fields don't need a universe to exist. They may exist independently of space-time. They may be eternal, infinite, primordial. Which means the trigger that created our universe may have been embedded in a deeper reality that has always existed, a reality with no beginning, no end, no creation. just permanent potential, occasionally giving birth to universes. If a quantum field can create one universe, it can create many. Inflation doesn't necessarily happen once. It may be happening continuously, endlessly, eternally, in a vast cosmic landscape of possibilities. In some regions, universes balloon into existence. In others, universes collapse. Some universes may contain familiar physics. Others may operate by entirely different laws, different particles, different forces, different dimensions. Our universe, then, might be one bubble in a vast cosmic foam, one leaf among infinitely many in an eternal cosmic tree, one spark in a field of endless creation. And here's the astonishing part. Some physicists believe we might be able to detect the existence of other universes. How? Through collisions. If two universe bubbles expand and collide, they might leave scars, circular temperature patterns, in the cosmic microwave background. A few of these patterns have already been observed. Are they proof? Not yet, but they are hints, glimmers, possibilities that whisper of worlds beyond our own. If this is true, then our universe did have a before, but not a single one, not a moment, not a snapshot. The before becomes an infinite ocean of universes expanding, colliding, birthing new universes, a cosmic landscape larger than anything we can imagine. Let's slow down for a moment, because all of this can feel overwhelming. So much speculation, so many possibilities, so many ways the universe might have come into existence. But each idea leads us back to one deep truth. The Big Bang is not the beginning. It is a boundary, a horizon, a veil. Just as the surface of the ocean hides the depths below it, the Big Bang hides the deeper structure of reality beneath our universe. Was there a previous universe? Was there an eternal quantum vacuum? Was there a timeless mathematical realm? Was there a cycle of birth and rebirth? Or was there something else, something stranger, something we haven't imagined yet because our minds are still bound by the physics of this universe? Whatever existed before our universe, one thing is certain: we are connected to it. Every particle in your body, every atom in every star, every photon crossing the cosmic void, all of it emerged from the transition that happened at the Big Bang. A transition shaped by whatever came before. A transition influenced by states and forces and realities that existed beyond time. To understand the universe, we must understand the canvas it was painted on. To understand ourselves, we must understand the origins of the space we inhabit. And the deeper we look, the more the universe seems to be telling us that our beginning wasn't the first beginning. Not by a long shot. As we wander further into this question of what came before the universe, we begin to encounter ideas that don't just challenge physics, they challenge our intuition, our sense of time, our understanding of reality. And perhaps the most thought-provoking idea of all is that our universe carries faint echoes from a universe that existed long before ours. These echoes wouldn't be obvious. They wouldn't be loud. They wouldn't appear in the form of messages or symbols or anything we might recognize. Instead, they would appear as tiny irregularities, subtle asymmetries, patterns in the oldest light in the cosmos, a kind of cosmic archaeology, fossils not made of bone or stone, but of energy. One of the most intriguing of these patterns is known as the cold spot, a large region of the cosmic microwave background that is significantly colder than surrounding regions. It shouldn't be there, not according to our standard model. The universe should be almost perfectly uniform at this scale, smooth, even, balanced. And yet, the cold spot exists. The simplest explanation is that it's a statistical fluke, something that happened by chance. But some physicists believe it might be something more. A bruise left by a collision between our universe and another. A mark from a time before the Big Bang, preserved in the cosmic radiation like a fingerprint. If this is true, then the cold spot is not just an anomaly. It is a message. Not a message written for us, but a message written by nature itself, telling us that our universe once brushed against another, that our cosmos, vast as it is not alone, that we emerged from a larger, more ancient reality. One of the most elegant attempts to describe this deeper reality comes from the mathematician Roger Penrose. His idea is called conformal cyclic cosmology, and it begins with a simple but astonishing claim. Universes have life cycles. They are born, they expand, they grow old, and they fade away. And when one universe ends, another begins. Not in a violent collapse, but in a gentle, seamless transition, like the passing of an era. In this picture, what we call the Big Bang wasn't the first universe springing into existence. It was the latest in a long sequence of universes, each one emerging from the last. Penrose calls these universes eons. Each eon gives birth to the next, in an infinite chain that stretches forward and backward forever. And here's the remarkable part. If Penrose is right, our universe should contain faint traces of the eon that came before, fossils from a previous cosmic era, patterns engraved in the cosmic microwave background by events that happened before our universe began. Penrose claims to have found some of these patterns, extremely subtle rings in the background radiation, signatures he believes were caused by the final explosions of black holes in the prior universe. Imagine that. Black holes from a universe long gone, sending out bursts of energy that reached across an unfathomable cosmic boundary and left marks in our universe's very first moments. Echoes of a world that no longer exists. Are these rings real? Are they definitive proof? No. The evidence is controversial. The scientific community is divided. But the possibility is breathtaking. Because if these rings truly exist, if they truly come from a previous eon, then it means our universe had a parent, a predecessor, a history older than time itself. One of the deepest mysteries in physics is the nature of information. When matter falls into a black hole, does the information that defines it disappear? Or is it somehow preserved? For decades, scientists believed black holes destroyed information completely, erasing the history of whatever fell inside. But today, many physicists believe the opposite. Information is never lost. It can be scrambled, transformed, encoded, but not erased. If information truly survives, then the end of a universe, with all its black holes evaporating over trillions upon trillions of years, might not wipe its history clean. Instead, that information may leak out slowly, through Hawking radiation or through deeper quantum processes we don't yet fully understand. And if that information can survive the end of a universe, it might play a role in the birth of the next. This idea is speculative. It's bold. It stretches the imagination. But it is grounded in real physics, in the belief that information is a fundamental part of reality, as essential as space, time, and energy. Imagine a universe arising not from emptiness, but from the reorganized, reprocessed information of an older world. Not a copy, but a descendant, a continuation, a legacy written into the structure of space-time itself. There is another possibility, one that links two of the strangest objects in physics, the Big Bang and black holes. Inside a black hole, space-time collapses toward a singularity. But some theories propose that this collapse might not be the end. Instead, the singularity could be a bridge, a connection to a new region of space-time, a doorway to a new universe. If this is true, then our universe might be the interior of a black hole in another universe, a bubble of space-time connected through a wormhole-like structure, a universe inside a universe. This idea, once dismissed as too exotic, is gaining traction as physicists explore quantum gravity. Because black holes and the Big Bang share mathematical similarities, both describe regions where normal physics breaks down. Both involve extreme densities. Both involve boundaries beyond which we cannot see. Perhaps the birth of a universe is simply what happens when the gravitational collapse of matter in an older universe reaches a critical point. Not a dead end, but a new beginning. a rebirth through a cosmic tunnel. And if this is true, then the before of our universe is not a mystical realm or a distant eon. It is simply elsewhere. A place where time flows differently. A place hidden behind an event horizon. A place governed by different forces and different laws. A place we cannot access, but that may be as real as the universe we inhabit now. By now, the question, what came before the Big Bang, has transformed into something much larger, much stranger, much more profound. Because the deeper we go, the clearer it becomes that the Big Bang is not the beginning at all. It is a bridge, a transition, a doorway between realities. What came before our universe might be another universe in a long cosmic chain, a quantum vacuum with infinite potential, a collapsing star in a parent universe, an eternal field generating endless universes, a previous eon whose traces linger in our cosmic background. Or it might be something else entirely, something none of our theories have captured yet, something outside the boundaries of imagination. Whatever existed before the Big Bang, one thing is certain: our universe is not an isolated miracle. It is part of a larger, deeper, more mysterious reality. A reality that existed long before us, and a reality that will continue long after we are gone. As we continue to peel back the layers of this ancient mystery, we encounter an idea that may be the most difficult of all to grasp. The idea that before the universe existed, before the Big Bang, before space and gravity and fields and fluctuations, there was no time. Not empty time, not a stretch of duration waiting for the universe to appear, not a quiet pause before creation, but the complete absence of time itself. This idea is one of the deepest conclusions of modern cosmology, that time, the thing we use to measure everything in our lives, the thing that flows from moment to moment, didn't exist before the Big Bang. Not because it was hidden, not because it was frozen, but because the universe had not yet created the conditions that make time possible. It's hard to wrap your mind around this. Time feels so fundamental, so unavoidable, so woven into our experience that imagining its absence is almost impossible. How can something begin if there is no time? How can a process unfold? How can anything exist? But according to general relativity, time and space are inseparable. They are part of the same fabric, a single entity called space-time. And space-time, according to the standard model of cosmology, came into existence at the moment of the Big Bang. Before space-time exists, the question, what came before, has no meaning, because before is a time-dependent concept. Without time, there is no earlier, no later, no sequence. Just a timeless state from which the universe emerges like a wave rising from a vast, silent ocean. This idea is often misunderstood as saying the universe came from nothing. But that's not quite right, because the nothing of physics is not an empty void. It is a state without space, without matter, without energy, but not without laws. On Thomas. Not without structure, not without deep mathematical relationships that may themselves be eternal. A timeless realm can still exist. It simply doesn't change, not because it cannot, but because change requires time. Imagine a painting, a perfect still image. It doesn't change, it doesn't evolve, it doesn't move, but it exists. It has structure, it has form, it contains information. And if someone were to animate that painting, each frame could unfold into a sequence, a narrative, a story, a universe. The timeless state before the universe may be something like that, a static, eternal mathematical reality from which time emerges as a result of the laws encoded within it. Some physicists propose that the universe began when a timeless quantum state transitioned into a dynamic one, when the underlying mathematical structure unfrozen and allowed change to occur. This unfreezing, might be what we call the Big Bang. Not an explosion, not a burst, but a shift in the nature of reality, from timelessness to time, from stillness to motion, from potential to unfolding. If this idea is correct, then the question, what came before, is like asking, what happened before the first frame of a movie? The true answer might be, the frames were always there. They simply weren't playing yet. Time is not a river flowing independently of the universe. It is a property of the universe. It is woven into the fabric of reality. And like any property, it can emerge. It can appear. It can begin. This brings us to one of the oldest questions in philosophy and physics. Why does anything exist at all? Why is there something instead of nothing? Where did the laws of physics come from? Why do they have the values they do? Why is the universe structured in a way that allows complexity, life, consciousness? If the universe emerged from a timeless mathematical realm, then the reason may lie not in causation, because causation requires time, but in structure, in symmetry, in inevitability. Perhaps a reality with no universe is less stable than one with a universe. Perhaps the equations governing the quantum vacuum naturally lead to expansion. Perhaps universes are the default state, not the exception. Perhaps existence is simply what the underlying mathematics does. Or perhaps even deeper still, perhaps the universe exists because consciousness exists. Or consciousness exists because the universe exists. Or perhaps both arise from the same fundamental structure that lies beneath space, time, and physics. These ideas are not scientific conclusions. They are possibilities, but they reflect the direction our understanding is moving in. The more we uncover about the universe, the more it seems to point toward a foundational reality beyond space-time. A reality where the distinction between something and nothing begins to blur. We are accustomed to thinking of time as linear, flowing from past to present to future. But in extreme conditions, time behaves differently. Near black holes, time slows down. In the early universe, time may have stretched or compressed. In quantum gravity, time may not exist at all. It may be an emergent illusion, something that appears only when the universe reaches a certain scale or complexity. Near the Big Bang, our usual understanding of time collapses. Our seconds, minutes, hours, and years, the units we measure our lives with, lose their meaning. There is no flow, no before, no after. There is only a strange transitional state from which time emerges like a mist from a still pond. This suggests something profound. Time may not be a fundamental feature of reality. It may be a property of the universe that appears when certain conditions are met. And if time can appear, it can also disappear. It can dissolve. It can return to the timeless state from which it came. In fact, some models predict that the far future of the universe, trillions upon trillions of years from now, might become timeless again. When all matter decays, when all black holes evaporate, when the universe becomes cold and empty, time itself may lose meaning. The universe may return to a state much like the one before the Big Bang, not because it collapses, but because nothing changes anymore. And from that timeless stillness, a new universe may emerge. At this point, something becomes clear. The Big Bang was not the beginning of everything. It was the beginning of our version of everything. Our space-time, our laws, our flow of time, our physical story. But the deeper reality, the structure beneath it, may be timeless, eternal, unchanging. A realm from which universes arise the way waves rise from the sea. In this view, the Big Bang is not the first page of the cosmic book. It is simply the first page of our chapter. The story began long before that page, in ways we are only beginning to imagine. As we travel deeper into this mystery of what came before the Big Bang, we encounter a possibility that is both astonishing and strangely intuitive once you sit with it. A possibility that suggests the universe didn't emerge from a substance, or a field, or a previous universe, but from something far more abstract, yet far more fundamental: mathematics. This idea, called the mathematical universe hypothesis, proposes something profound: that the universe is not described by mathematics, it is mathematics. That the structure of reality is fundamentally numerical, relational, geometric. That every particle, every force, every dimension, every moment is part of an enormous mathematical object existing outside of time. If this is true, then the Big Bang wasn't a physical creation so much as a transition. A moment when a particular mathematical structure, the one that encodes our universe, became instantiated as a physical reality. A moment when the static became dynamic, when possibility became experience. In this picture, the question, "What came before the universe?" shifts from a physical question to a conceptual one. Because a mathematical structure doesn't exist in time, it doesn't change, it doesn't evolve, it simply is. Eternal, unmoving, complete. Our universe, then, may be what happens when consciousness travels through this structure, experiencing it as a sequence, the way you experience the frames of a film one after another, even though the entire film exists at once. Time, in this view, is a path. The universe is a landscape, and the Big Bang is simply the first step along that path. What makes this idea compelling is that the laws of physics truly are mathematical in nature, not metaphorically, but literally. Gravity is geometry, electromagnetism is topology, quantum mechanics is probability theory. The universe has structure, symmetry, constraints, and elegant rules that resemble nothing so much as a vast, multidimensional equation. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible, that the human brain, made of atoms forged in stars, can understand the deep laws that govern all of reality. Why should that be the case? Why should the universe obey simple, elegant mathematical laws? Why should reality be orderly at all? One answer is that the universe didn't choose to be mathematical. It emerged from mathematics. It is one possible solution to a much larger structure, one self-consistent configuration within an infinite space of mathematical possibilities. In this view, the Big Bang was not the beginning of existence. It was the moment when a particular set of mathematical relationships transitioned into physical form, when the equations took on meaning, when the geometry became space, when the parameters became energy. And what existed before this transition? The mathematics itself, unchanging, timeless, perfectly still. This idea leads to a radical possibility. If the universe is a mathematical structure, then other universes, other structures, might exist as well. Not off in distant regions of space, but in an abstract realm of possibilities. Universes built from different equations, different symmetries, different dimensionality. Universes where physics behaves in ways we cannot imagine because our laws are just one solution among infinite options. In this sense, before the Big Bang becomes meaningless, because the deeper reality, the mathematical realm, is not something that has a beginning. It doesn't start or end. It doesn't evolve. It simply is. All universes, including ours, may arise from this timeless landscape, each one a different expression of underlying mathematical truths. One of the most astonishing ideas in modern theoretical physics is that space-time itself may be emergent, not fundamental. That space and time themselves may arise from something deeper, just as temperature arises from the motion of molecules, or solidity arises from atomic forces. At the smallest scales, beneath the Planck length, space-time may dissolve into something more primitive, a network of relationships, a grid of interactions, a web of information, a purely mathematical structure without shape, without size, without time. In this view, the Big Bang was the moment when this abstract structure became dense enough, rich enough, complex enough to give rise to space-time as we know it, when the mathematics condensed into geometry, when change became possible, when time began. This means the real question is not what came before the Big Bang, but what kind of structure allowed the Big Bang to happen? What rules? What symmetries? What relationships? What equations? And why did this universe emerge rather than another? Perhaps the answer is anthropic, meaning only certain mathematical structures allow consciousness to exist, and we live in one of them. Or perhaps the answer is deeper, hidden in the nature of mathematics itself. In a purely mathematical universe, consciousness plays a strange role. It doesn't create the universe, but it might be required to interpret it. A mathematical structure doesn't run unless there is something, a mind, moving through it, experiencing it one frame at a time. This leads to a remarkable possibility. The universe unfolds not because time exists independently, but because consciousness moves along a path through the structure of reality. The universe is static, but our experience of it is dynamic. The Big Bang, then, may not have been the birth of the universe, only the birth of the part of the universe that can be experienced. The region where conscious observers can exist, the frame in the mathematical structure where time begins for beings like us. If mathematics existed before the universe, then the before of our universe isn't a physical state, but a conceptual one. It is the framework upon which physics is built, the foundation beneath the cosmic ocean, the silent architecture underlying everything. And this framework may be eternal, infinite, unchanging, a realm where the distinction between existence and non-existence becomes irrelevant, a realm where all possibilities exist at once, not physically, but conceptually, a realm from which universes emerge the way solutions emerge from equations. If this is true, then the Big Bang is not the creation of something from nothing. It is the moment when something that always existed gained the capacity to be experienced. A moment when a timeless structure became a living universe. A moment when mathematics became reality. Before the universe began, we imagine there must have been a place, a location, a backdrop against which creation unfolded. But this intuition, as natural as it feels, is wrong. Because according to modern physics, space itself is not a stage. It is an actor, a participant, a dynamic entity that can stretch, bend, ripple, and curve. Something that has properties, behaviors, and energy. Something that evolves. Which leads to a profound question: where did space come from? What existed before the cosmic fabric was woven? What was the universe when there was no here and no there? To answer this, we must follow the thread of physics to its smallest scales, far smaller than atoms, far smaller than quarks, far smaller than anything our instruments can probe, into the realm of quantum gravity, the place where the familiar laws of nature dissolve and a deeper structure begins to emerge. At the test-thisist scales imaginable, the Planck scale, space-time stops behaving like a smooth surface. It becomes turbulent, chaotic, a frothing sea of fluctuations known as quantum foam. Bubbles of space-time pop in and out of existence. Tiny wormholes open and close in unimaginably small timescales. Distances and durations lose their meaning. Geometry becomes probabilistic. This quantum foam may be the real foundation of the universe. Not space, not time, not matter, but a shifting, vibrating sea of microscopic geometry. And perhaps even geometry is not fundamental. Perhaps beneath the foam lies something more abstract. A network, a graph, a web of relationships, a mathematical blueprint from which the foam emerges. If this is true, then the Big Bang was not the creation of space. It was the moment the quantum foam expanded, smoothed, and stabilized into the vast cosmic fabric we inhabit. a transition from the wild, stormy realm of quantum gravity to the calm, continuous space-time we experience every day. One of the leading attempts to describe this deeper structure is called loop quantum gravity. It proposes that space is not continuous. Instead, it is made of tiny, discrete units, atoms of geometry, woven together by mathematical relationships. These building blocks are unimaginably small, so small that they are effectively invisible to us, but they combine to create everything we call space. In this picture, the Big Bang wasn't a singularity at all. It was a bounce, a transition from a previous state where space was contracting to the state where space began expanding, a collapse that reached a minimal volume, not zero, and then rebounded outward. If this is correct, then the universe existed before the Big Bang, not in the way we experience it now, not with stars or galaxies or time as we know it, but as a quantum gravitational state, a compact configuration of space atoms that collapsed, bounced, and expanded again. This would mean the Big Bang was not the birth of everything. It was simply the moment the universe became large enough and smooth enough for the familiar laws of physics to apply. The moment the quantum fog became the cosmic sky. Another path toward understanding the origin of space comes from string theory. According to this view, the smallest building blocks of reality are not particles or atoms of geometry, but tiny vibrating strings, one-dimensional loops whose oscillations give rise to the properties of particles. In this theory, space itself may arise from the collective behavior of strings. Dimensions unfold from vibration patterns. Forces emerge from resonances. And the Big Bang may have been the moment when these strings entered a new phase. A moment when the configuration of dimensions shifted, when the geometry of the universe reorganized itself into the form we inhabit. String theory even suggests the existence of extra dimensions, hidden, curled-up spaces that existed before and during the Big Bang, influencing its dynamics in ways we cannot yet observe. If this is true, then the before of the Big Bang may be encoded in the structure of these extra dimensions, dimensions that still exist around us, silently shaping the physics we experience. In one branch of string theory, M theory, the universe may be a three-dimensional brain floating in a higher dimensional space, and the Big Bang might have been a collision, a moment when our brain collided with another brain in this higher dimensional realm. The energy released by this collision could have ignited a new universe, setting off a chain reaction of expansion and cosmic evolution. This idea is breathtaking not just because of its scale, but because of what it implies, that the before of our universe might be a place, a higher dimensional landscape full of brains drifting, vibrating, interacting. If brain collisions are real, then the Big Bang was not a beginning. It was an event, one of potentially many collisions that happen across the higher dimensional cosmos. And other universes, created by other collisions, may exist parallel to ours, beyond our observational horizon. What all these theories, loop quantum gravity, string theory, M theory, have in common is a profound shift in perspective. They suggest that space, the thing we take for granted every moment of our lives, is not fundamental. It is built, constructed, emergent, the result of deeper processes happening at scales far smaller than anything we can see. If space can emerge, then it can also vanish. If space can evolve, then it can begin. If space is not fundamental, then the Big Bang was not the birth of all existence, only the birth of space as we experience it. And if something exists beneath space, something deeper and more fundamental, then that something, whatever it is, existed before the universe. Not in space, not in time, but in a realm where the concept of before must be redefined. To the deeper we go, the more the question, what came before the Big Bang, transforms. It becomes clear that before may not be a point in time, but a state of reality, a configuration of fundamental structures, quantum, mathematical, geometric, that gave rise to the universe we inhabit. A state that still exists beneath everything, like the roots beneath a tree whose branches reach across billions of light years. If these ideas are correct, then the Big Bang wasn't the moment the universe began. It was the moment the universe became recognizable, the moment the stage was built, the moment the lights came on, the moment the script began. The deeper story, the one beneath time and space, is still waiting to be uncovered. As we reach the end of this journey, we find ourselves standing on the same question we began with, but everything feels different now. The simple question, what came before the Big Bang, has unfolded into a vast landscape of possibilities, each one stranger and more beautiful than the last. And yet, none of them feel like answers in the traditional sense. Instead, each possibility feels like a window, a direction, a way of seeing, a reminder that the truth of the universe may be larger than any single explanation, larger than our imagination, larger than our physics, larger than the very concept of beginnings. And that's the quiet beauty of this mystery. The deeper we go, the wider the universe becomes. The more we discover, the more we realize how much is left to explore. To understand the universe after the Big Bang, we often talk about the forces that shape it: gravity, electromagnetism, nuclear forces, quantum interactions. But these forces didn't exist as we know them at the moment of creation. They emerged. They crystallized out of the early universe the way ice forms from water, through a cooling, a transition, a breaking of symmetry. Before this symmetry broke, all forces may have been unified. All matter may have been identical. Physics itself may have been one single, elegant rule. Only when the universe expanded and cooled did it begin to differentiate, to become complex, rich, layered. This means the physics we experience is not fundamental. It is inherited. It is shaped by what came before, by the conditions of the earliest universe, and those conditions were shaped by something even deeper, by whatever existed prior to space-time, prior to expansion, prior to the universe we call our own. Our laws of physics are not fixed. They are emergent. They are the outcome of a cosmic history that stretches far beyond the limits of our vision. And so we return to a powerful idea, that our universe carries memories. Not conscious memories, not detailed stories, but imprints, patterns, structural echoes of whatever came before. Whether it was a prior universe in a long cosmic cycle, a quantum vacuum humming with potential, a higher dimensional realm of colliding brains, a mathematical landscape, or a timeless, changeless foundation beneath reality. Whatever came before left its fingerprints on the universe we see today. In the smoothness of the cosmic microwave background, in the distribution of galaxies across the sky, in the laws that govern particles and energy, in the very fabric of space itself. The universe is not a blank page. It is a continuation, a descendant, a story shaped by chapters we cannot read, but whose influence is everywhere. And this brings us to an important truth, one that is both humbling and freeing. There may be limits to what we can know, not because the universe hides its secrets maliciously, but because some of those secrets exist beyond the concepts our minds are built to grasp, beyond time, beyond space, beyond cause and effect. The boundary of the Big Bang is not a wall we can break through with bigger telescopes or more powerful equations. It is a conceptual horizon, the point where our familiar ideas lose meaning. And yet, this horizon is not the end of the story. It is the beginning of curiosity, the beginning of imagination, the beginning of a deeper understanding of what it means to exist in a universe that is far more mysterious than we once believed. When we explore questions like this, we are reminded of something profound, that human beings, fragile and temporary as we are, have the ability to wonder about the birth of the universe, to ask questions that stretch across billions of light years and trillions of years of time. to contemplate realities that existed long before stars and will continue long after they fade. This ability to question, to explore, to imagine is itself something extraordinary. We are made of matter forged in ancient stars, yet somehow we've become observers capable of trying to understand the universe that created us. And in moments like this, when we look not just into the cosmos but beyond its beginning, we see something remarkable. We are part of a story much larger than ourselves. A story that began long before the Earth formed, long before light filled the universe, long before time began to flow. A story whose first chapters may be forever out of reach, yet whose echoes we can still hear if we listen closely enough. If the universe emerged from a deeper reality, then perhaps it will return to one. Perhaps the universe is part of a cycle, or an equation, or an eternal sea of creation. Perhaps new universes are being born even now, expanding silently beyond our horizon. Perhaps this story has no true beginning and no true end. And in that realization, something shifts. The question, what came before the Big Bang, becomes something else entirely. It becomes an invitation to wonder, to imagine, to accept mystery as part of the beauty of existence. We may never know for certain what existed before our universe, but the search for that answer reveals something deeply meaningful. The universe is richer, deeper, and more mysterious than we can possibly comprehend, and we are privileged to be a small part of its unfolding story. So tonight, as we close this journey, let your thoughts drift gently across the vast cosmic ocean. Imagine the universe before our universe, the timeless realm beneath time, the structures beneath space, the echoes of worlds long gone, the possibilities beyond the horizon of understanding. Somewhere in that vast depth lies the answer, and perhaps the journey toward that answer is more important than the answer itself. Thank you for being here. Rest well, dream deeply, and let the universe hold you. Until next time.